Hi, and welcome to MA 212. Today we'll be talking about complex numbers. The first part of this is probably review for most of you, so we'll go through this fairly quickly. A complex number is any number in the form a plus bi. The variable for complex numbers usually gets written z. That's just convention. Here a and b are real numbers, and I is called the imaginary unit, and it has the property that I squared equals minus 1. The first part, a, is called the real part of z, and you write it like this: a equals re of z, and b is called the imaginary part. And an important thing to notice is that the imaginary part of z is b, and it's not bi. So for example, the real part of 3 plus 4i is 3, and the imaginary part of 3 plus 4i is 4. Okay. So complex numbers, the set of all complex numbers is called C. It's a big C. On the blackboard it'll look like this thing because I can't draw in bold. A complex number a plus 0i, well, that's just a real number. And a complex number in the form 0 plus bi, that's a pure imaginary number. It has no real part. Okay. Basic algebra of complex numbers. Again, this is probably review, but 3 plus 4i plus 7 minus 2i. Well, you add the real parts here, and you'll get 10, and you add the imaginary parts, and you'll get plus 2i. Multiplication works out the way you think it will also. You just sort of FOIL things. Here's an example for you: 2 minus 3i times negative 1 plus 6i. You FOIL everything, and then you use the property that I squared is negative 1, and you'll end up with 9 plus 20i. Another example, 2i times 1 plus 4i. Well, I distribute through, and I'll get 2i plus 8i squared, and you'll end up with negative 8 plus 2i. We've already talked about complex conjugates in class. The complex conjugate of a plus bi, you write that as z bar, and it's a minus bi. So let's see. So for example, the complex conjugate of 3 plus 4i, its conjugate would be 3 minus 4i. And if you check, you can notice that if you add up if you add a complex number and its conjugate, you'll get 2 times the real part of z. You can check and see that if you get, or z minus z bar will be 2bi. Okay. Also, you can check and see that if you multiply a number by its complex conjugate, you get a purely real number. So division, we've done a couple examples of division in class also. Again, the trick here, so this is a perfectly good number, negative 3 plus 2i over 7 minus 4i. It's just not in the standard form for a complex number, so the thing we do is multiply by the conjugate here. So for example, if I want to take 1 plus I over 2 minus 3i, what I'll do is multiply everything by the conjugate of 2 minus 3i, which is 2 plus 3i, over 2 plus 3i. I multiply out the top, and I get 2 plus 2i plus 3i plus 3i squared. On the bottom, I'll end up with 4 minus 6i plus 6i minus 9i squared. On the top, I end up with what? Remember that this is now negative 3, so I'll end up with negative 1 plus 5i. On the bottom, my imaginary parts cancel. I get 13. So this ends up being negative 1 over 13 plus 5 over 13i. Okay. One final thing to notice, there are 4 possibilities for integer powers of I. Notice that I to the 0th power, well, just like any other number, you get 1. I to the first power is, that's I, not 1. I squared is negative 1 by definition. And I cubed, well, that's I squared times I, so that's negative 1 times I, so that's negative I. And then this pattern continues for after this. So like I to the fourth will be I squared times I squared, and that's going to be negative 1 times negative 1, so that's equal to 1. So I to the fourth is the same as I to the 0th power. I to the fifth is going to be I to the fourth times I, so that's going to be just I, and so on and so forth. Okay, so I shouldn't see you leaving any answers with powers of I in there. You should be simplifying everything. Okay, so the important part of today's video is Euler's formula. Probably the most important part anyway. So, historical note, this is named after man, Leonhard Euler. He's a Swiss mathematician, extremely talented. The name Euler is pronounced just like that, Euler. It's not Euler. Don't say Euler, okay? It's Euler. Okay. Remember these formulas from Calc 2. You remember the Taylor series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus so on and so forth. And these are the Taylor series for cosine x and for sine x. Cosine x is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial, and so on and so forth. And there's a similar Taylor series for sine of x. What I'd like to do is just go ahead and compute e to the iy using Taylor series, okay? So it's not exactly clear that we can do this because the Taylor series from calculus are for real numbers, and here we're plugging in an imaginary or a complex number. But let's just go with it and see what we have to say. We see that e to the iy, well, if we follow the Taylor series for e to the x, we'll end up with 1 plus our iy plus iy squared over 2 factorial plus iy cubed over 3 factorial plus iy to the 4 over 4 factorial plus, I know this is a lot of terms, but I need them all in order to get the pattern to work out. Okay, so there we've got the Taylor series for e to the iy. We just wrote it down. We substituted in iy for x. Let's go ahead and simplify this a little bit. So this is 1 plus iy plus I'll have I squared y, so I'll end up at minus y squared over 2 factorial. Here I'll have an I cubed y cubed, so that's minus I y cubed over 3 factorial. Here I'll have I to the fourth y to the fourth, so that's a plus y to the 4 over 4 factorial. The next term is I to the fifth, that's plus iy to the 5 over 5 factorial. I to the sixth, that's the same thing as I squared, so that's minus y to the 6 over 6 factorial. My I to the seventh is the same thing as I cubed, and that's minus I y to the 7 over 7 factorial, and so on and so forth. So now let's just group terms a little bit. This is 1 minus y squared over 2 factorial plus y to the 4 over 4 factorial minus y to the 6 over 6 factorial. And this pattern will keep going. Plus I times, if I factor things out, I'll get a y here, minus y cubed over 3 factorial plus y to the 5 over 5 factorial minus y to the 7 over 7 factorial. And this pattern keeps going. If we compare these two series to the series for cosine and sine, we can see that this one is really just the cosine of y, and this guy is sine of y. So I could write this is cosine of y plus I sine of y. Okay, and this is just amazing. This tells us how to take e to a complex number and write it in terms of sines and cosines. Okay, so notice, what's this mean? This means that e to the I pi is cosine pi plus I sine pi, which is -1. This is just incredible, right? So e to a irrational, purely imaginary number turns out to be -1. Crazy. Okay. Notice that then what also has to be true is for any integer k, e to the 2 pi I k must be cosine of 2 pi k plus I sine 2 pi k. You also get 1 out of that. Okay. So if we combine this, we get Euler's formula. Okay. If we take e to a complex number, so a number in the form x plus iy, well, let's use the usual laws of exponents. That's e to the x times e to the iy. E to the iy we can expand. Oops, I'm running low on battery. And I get e to the x times cosine y plus I sine y, and then I can expand that out and get e to the x cosine y plus I times e to the x sine y. This is called Euler's formula, and it is we're gonna do a lot of work with this in the future. It's important. Okay. So Euler's formula gives us a way to write numbers in what's called polar form and in rectangular form. So let's see. Here's a fact for you. Any number in the form a plus bi, you can represent it in the form r e to the I theta, where r and theta are real numbers, and r is bigger than 0. Okay. If I write it in the form a plus bi, that's called the rectangular form. And if I write it in r e to the I theta, that's called the polar form of z. Okay, so the conversion between rectangular and polar forms, it's the exact same as the conversion between rectangular and polar coordinates that you did in Calc 3. Okay, so it's easy enough. If we have a complex number, r e to the I theta, and that's in polar form, and I want to express it in rectangular form, it's easy enough. So for example, suppose I have 3e to the pi over 4i. This would be the number in polar form. If I use Euler's formula, that tells me it's 3 times cosine pi over 4 plus I sine pi over 4. So that's going to give me 3 root 2 over 2 plus 3 root 2 over 2i. And that's it. Now our number is in rectangular form. Okay. On the other hand, if we want to go from rectangular to polar, we can do that also. Okay. So suppose I have a number in the form, well, let's just do this in general. So suppose I have a plus bi, and I want to write that in the form re to the I theta, where r is bigger than 0, or equal to. Okay, well, what's this tell us? This tells us that a plus bi must be equal to r cosine theta plus ir sine theta. Okay. So, what's this say? This says that my a must be r cos theta. My b has to be r sine theta, right? I'm just equating. Here's the real part. It has to match that. Here's the imaginary part. Has to match that. Okay. If I go ahead and square these two and add them, a squared plus b squared, that should give me r squared cos squared theta plus r squared sine squared theta. So that should give me, what, a squared plus b squared on the left, and that gives me r squared on the right. So I can see that my r has to be the square root of a squared plus b squared. Okay, if I take a over b, what else can I get? I can get, well, let's take b over a. If I take b over a, that must be sine theta over tan theta, or oops, I jumped ahead of myself. Sine theta over cos theta. So that means that b over a has to be tan of theta. Okay, if you check carefully, you can see that, what? We have to have tangent of theta be b over a, but there's lots of choices for theta. Okay? All we have to do is make sure that we get our theta in the appropriate quadrant. Okay? So for example, if my complex number is in the first quadrant, then my theta should be between 0 and pi over 4. If my complex number is in the second quadrant, then my complex number needs to be between pi over 2 and pi. Third quadrant, pi to 3 pi over 2, and so on and so forth. Okay? So that's it. So for, let's do an example, a concrete example. So if my complex number is this one, negative root 2 over 2 plus root 2 over 2i, what do we need to do? We need to choose our r. I'm really running low on battery here. What's my r equal to? It's the square root of, I square the first guy and I get 2 over 4, and the second one is 2 over 4, so that's the square root of 1, so that's 1. And what else do I have? I have to have tan of theta be 1, right? It has to be negative 1. And so I'm going to take my theta to be what? It'll be 5 pi over 4 in order to get my, what do I need? I need the cosine term. I need the cos of theta to turn out to be negative in order to get this first guy to work out okay. Okay. Let's talk some more about complex numbers. One of the great things about complex numbers is that it allows us to solve polynomials. Okay, so we've all seen the quadratic equation. If I want to find the roots of a quadratic equation, I use the quadratic formula, and well, that's about it. Okay, as long as we're solving equations, I might want to find all the complex solutions to an equation like this. I might want to solve x to the nth power equals 1. Okay. Now we know that if n is even, then negative 1 and 1 are the only solutions to this equation, and if n is odd, then 1 is the only real solution to this equation. But what about complex solutions to this equation? Okay. The complex solutions to this equation are called the roots of unity, or the nth roots of unity. Okay, so let's see. For example, in the case n equals 4, we can check and see that 1, negative 1, I, and minus I, they're all solutions to x to the 4th equals 1. How can we do this in general? Well, we can consider solving x to the nth power equals 1. And let's go ahead and just write x in its polar form, r e to the I theta, where r and theta are real numbers and r is bigger or equal to 0. Then x to the n equals 1 means that r e to the I theta to the nth power equals 1. That's r to the n e to the I n theta equals 1. And now I can use Euler's formula. This means that r to the n cos of n theta plus I sine of n theta must be 1. So r to the n cos n theta plus I r to the n sine n theta has to be 1. If I look at the left side of the equation, I see that this number right here is purely real. Okay, r is a real number, n is a real number, theta is a real number, that guy is real, and this guy is purely imaginary. Now I want to choose r and theta such that the guy on the left is equal to the thing on the right. Now on the right there is no imaginary parts, so what do we need? We need Rn sine of n theta to be 0, and we need r to the nth power cosine of n theta to be 1. How can we do this? Well, if we think about it for a minute, we can see that what we need the sine n theta term to be 0, we need r to be 1, and we need to choose, we need to make sure that cosine theta is equal to 1. Okay, so we need to choose theta such that the sine n theta is equal to 0 and the cosine theta is equal to 1. Well, that means that n theta needs to be 0, or n theta could be 2 pi, that would work, or n theta could be 4 pi, that would work, or n theta could be 6 pi, that would also work. Okay, each one of these different choices of theta gives us hopefully a different solution to our equation. Okay, what's the first choice of theta tell us? That tells us theta equals 0. The second choice tells us theta equals 2 pi over n. The third one tells us theta equals 4 pi over n. The next one is theta equals 6 pi over n, and so on and so forth. Okay, so x equals e to the I times, what's this pattern? This is 2 pi times some integer, any integer over n, is a solution to x to the n equals 1 for any k. If we check though, we'll start when we calculate what e to the 2 pi k over ni is. When we start calculating that, like in rectangular form, we'll see that after k gets big enough, we start repeating ourselves. There's only actually n distinct solutions here. Okay? That's all summed up right here. There are nth roots of unity. Nth roots of unity are solutions to this equation. They are e to the 0 pi I over n, e to the 2 pi I over n, e to the 4 pi I over n, and you keep going until you get to 2n minus 2 pi I over n. Okay? So for example, the cube roots of unity, those are the solutions to x cubed minus 1 equals 0. Those are the solutions to that are e to the 0 pi I over 3, e to the 2 pi I over 3, and e to the 4 pi I over 3. Okay, that's it. We can write those out in rectangular coordinates using Euler's formula as such, and that's it. It's actually fun. You can go ahead and multiply out these numbers in Cartesian coordinates and just FOIL them out, and you do get one, and it's just sort of fun to see it work out. Okay, yeah, this just says that x1 and x2 are the cube roots of unity, and that's it. That is our whirlwind tour through complex numbers.